So in our previous lecture, we learned that action potentials propagating across the plasma membrane of a contractile cell will initiate the actual contraction. So in this lecture, we're going to take a look at those action potentials because the action potentials that occur in a contractile myocardial cell are quite different than any of the action potentials that you've seen so far. So on the screen, I have an action potential for a neuron. And one of the things that we've said about action potentials is that there's a rapid depolarization followed by a rapid repolarization. And that's certainly true for the neuron, and that's true for a skeletal muscle fiber. In cardiac cells, action potentials are different. And in fact, contractile cells and autorhythmic cells even have different action potentials. But this lecture is going to focus on the contractile cells. Now remember, the point of the action potential is to trigger the start of the excitation-contraction coupling that's going to lead to the contraction of the myocardial cell, which is part of the heartbeat, or the heart contraction and moving blood. This particular action potential is probably the most complicated one that we will cover, and so we're going to do it in a couple different ways. The first thing that I'm going to do is I'm going to show you the tracing. I'm going to show you what this action potential looks like. Then I'm going to introduce some key players. So just like we tell every story, we start with kind of a character biography. Who are the characters and what are they doing and what are their personality traits? And the same thing is going to be true here. And then I'm going to take you over to a PowerPoint where you're going to see these gated channels and leak channels in action as the tracing of the action potential happens on the side. And then finally, we'll take a look at some features of this action potential as it relates to twitches. All right, so the first thing I want to do is I want to diagram the action potential tracing for a contractile cell. So this represents the neuron, and this is going to be the contractile cell. Now, the first thing that we need to do is change our time. Typically, action potentials are between 2 and 4 milliseconds. However, the action potential of a contractile cell is 250 milliseconds. You heard that right. Much, much longer. The tracing is also quite different. You can draw this out now if you'd like, or you can draw it out later when we talk about the steps in more detail. But the tracing is quite different. First of all, our resting membrane potential is -90. When we do get rapid depolarization, it looks like it's going to be straight up. It's not really straight up, but look at what we're trying to do. We're trying to crunch 250 milliseconds onto the same length of my x-axis. And so therefore, when I crunch my depolarization down, it no longer has a nice slant to it. It looks straight up. Then things get really interesting. We get this little bump here, and then we get something called a plateau, and then eventually it kind of falls back like so. So that's the action potential. It's very long. The depolarization and the repolarization are separated by a long period of time kind of above zero, where it looks like the membrane potential plateaus out. All right, now that I've hopefully piqued your interest on what the heck is going on, let's introduce some key characters. First, let's address the resting membrane potential. So -90 millivolts should definitely pique your interest as a number that we've seen before. And we've seen it in relationship to potassium. When we talked about the Nernst equation and the predicted electrochemical equilibrium, we said that if only potassium was allowed to reach its electrochemical equilibrium, then the membrane potential would be -90. Well, here we see -90, so what does that mean? That means that only potassium is allowed to reach its electrochemical equilibrium. And that is because there are virtually 0 sodium leak channels. So we're just going to simplify this and say 0. So because there are no sodium leak channels, only potassium contributes to the resting membrane potential through leak channels. So this is definitely different from the neuron. Now let's introduce our voltage-sensitive gated channels. There are 3 of them. So the first one is one we've seen before. This is our double-gated sodium channel. And these are all voltage sensitive. So our double-gated sodium channel behaves as follows. It opens rapidly in response to depolarization, but also closes very rapidly. In addition, we have a calcium channel. Yep, you heard that right. A calcium channel. It's actually one we saw in the previous lecture. It is the L-type calcium channel. So in the previous lecture, when we looked at excitation-contraction coupling, we introduced an L-type calcium channel, and I didn't tell you what L stands for. L stands for long. This is a voltage-sensitive calcium channel. Again, these are all voltage-sensitive. That opens in response to depolarization, but it's very slow to open. It takes quite a bit of time before it decides to open, and then when it opens, it stays open for a really long time, between 150 and 200 milliseconds. That's much longer than the sodium channel, which is only open for half a millisecond. So the L-type calcium channel is going to play a role in the action potential here. And then our last one is potassium. So here's where things get even stranger. There are actually multiple different types of voltage-sensitive potassium gates. However, this is already complicated enough. So what I'm going to do is create a composite. Am I lying a little bit? I am. But it will help you understand what's going on. So what is a composite? Sometimes when you read a story or a story goes from a book to the silver screen, you will have composite characters. You will create one character that's really a mesh of multiple characters that fill a role to drive a plot forward. And in the same way, we are going to create a composite voltage-sensitive potassium gate. It's just going to be one, and it's going to basically mimic the behaviors of all of the potassium gates that are important. So it's voltage-sensitive. The default position of this voltage-sensitive potassium gate is to be open. So this is new for us. We've not seen this before, to have an open potassium-gated channel. As long as the membrane potential is in negative territory, so below 0, the gate is open. But when the membrane potential goes above 0, so it shoots up and depolarizes into positive territory, the gate closes. So we're just going to call this a special potassium-gated channel. Since the voltage determines the position of the gate, this is clearly a voltage-sensitive channel as well. All right, let's see this in action. So now let's go ahead and tell our story. This is a PowerPoint presentation that I created specifically for this class. It is available to you on Canvas if you are enrolled in this class, and you can download it and play it just like I'm playing it at your leisure. So we're going to insert the various characters or players in our action potential in this membrane. But first, let's talk about the leak channels. As stated, the contractile cells have a resting membrane potential of minus 90 millivolts, not minus 70 millivolts like we see in the neuron. And the main reason why the resting membrane potential is at minus 90 here is because there are almost no sodium leak channels. So for our purposes, we're going to assume there are 0 sodium leak channels and that the leak channels are exclusively for potassium. So there's our potassium leak channel. In addition, there are gated potassium channels, but our gated potassium channels are like channels we have never seen before. And in reality, I'm fudging a little bit here because I've created a voltage-sensitive potassium-gated channel that is really a composite of multiple different channel types. But the behavior of this composite channel is very predictable. Here is the rule. When the membrane potential is below 0, the gated channel for potassium is open. This is new. We've not seen anything like this before. Typically, the default position of a gated channel is to be closed. And here, I'm showing you that the gated channel is open as long as the membrane potential is below 0. But it is a voltage-sensitive channel. So when the membrane potential goes positive, so above 0, then the channel will close. So that's the way that this particular voltage-sensitive channel behaves. In addition, we have our old friend, the double-gated sodium channel, which rapidly opens in response to depolarization and rapidly closes as well. And we have our L-type calcium gates that were introduced in the previous lecture. Now, in the previous lecture, I did not spoil the fact that these are actually part of the action potential. They don't just exist in the membrane to let calcium in, although that's a major function, but they do also participate in the action potential itself. So these are our L-type calcium gates, and L stands for long time, which means that they are open for a long time, but they're slow. They do open in response to depolarization, but they take their sweet time doing so. All right, let's go ahead and start with our story. So we start with our story at rest. The resting membrane potential is minus 90 millivolts. Potassium reaches its electrochemical equilibrium using both leak channels and open gated channels. Remember, the membrane potential is below 0 here, so those gated channels are open. Now let's assume that we have a little bit of depolarization. What's going to happen next? Those sodium gates are going to rapidly open, and sodium is going to come flooding into the myocardial cell. What this will do is cause a rapid depolarization. As the membrane potential rapidly depolarizes, look at what's happening to these special potassium gates. They're starting to close because remember, their behavior is to close as the membrane potential moves into positive territory. So that means that potassium has fewer ways to move. And here, obviously, most of the movement is done by sodium. The sodium gates open rapidly, causing rapid depolarization, but then they also rapidly close. And so there's a brief period of time here where there are no gated channels open. It is simply just the potassium leak channel. So now that membrane potential is going to start drifting back down towards -90. It drifts in kind of a shallow tracing, but it still is drifting in that direction. But wait, our L-type calcium gates finally decide to get into the game, and those L-type calcium gates are going to open. So remember, L-type calcium gates are voltage sensitive. They respond to the depolarization, but they are slow to open. There's not nearly as much calcium in the extracellular fluid as there is sodium, so even when I open these calcium gates, only a little bit of calcium trickles in. And the amount of calcium that trickles in offsets or cancels out the amount of potassium that leaves through these leak channels, such that the membrane potential at this point plateaus or remains unchanged. So here you see a very long plateau where calcium influx is balanced by potassium efflux, and so the membrane potential remains unchanged. About 150 milliseconds after the calcium gates open, they finally decide to close, and then you have no open gated channels. They're all closed. So the only way any ion is going to move is through a leak channel. And so once again, we have a little potassium leaking out, and our membrane potential starts to dip down. Once our membrane potential dips down into negative territory, then our special voltage-sensitive potassium channels are going to reopen. This gives potassium a lot more options to reach its electrochemical equilibrium. So therefore, potassium has more opportunities to exit the cell, does so more rapidly, and we see a pretty rapid repolarization at this point. So this ends our action potential, but during the plateau phase, a little bit of calcium came in, and we know that the role of that calcium is twofold. Some of that calcium will bind to troponin directly, initiating cross bridges, and some of that calcium is going to trigger the release of a much larger amount of calcium from the sarcoplasmic reticulum, and this was covered in the previous lecture. So note that the twitch does not start until the L-type calcium gates open, because that's when we get our first exposure to calcium. So let's briefly map out some of these events on this tracing. Our resting membrane potential is -90, and that is because potassium has reached its electrochemical equilibrium through both leak channels and through the special voltage-sensitive potassium gates. We get a little bit of depolarization from the cell next door, and this triggers the voltage-sensitive sodium gates to open. About half a millisecond later, they close. And at that point, really there's no voltage-sensitive gates open. The only ions that are moving are potassium, and they're only moving through the leak channels. This causes a slight repolarization. But then the L-type calcium gates finally open, and we get our plateau phase, where calcium influx is balanced by potassium efflux. Once the L-type calcium gates close, then the membrane potential continues its drift downwards towards rest through the leak channels. Once the membrane potential falls below 0, then the special voltage-sensitive potassium gates are going to open. This provides more opportunity for potassium to move across that membrane, and therefore potassium moves out of the cell faster, causing a more rapid repolarization until potassium's electrochemical equilibrium is achieved. So many things in our body that seem especially cumbersome or unnecessary often serve a purpose, and the same thing is true here. First of all, we have an incredibly long action potential, and it involves calcium. The purpose of calcium hopefully is somewhat obvious at this point. Calcium comes in from the extracellular fluid, and that's really what starts the twitch. Some of it binds to troponin directly, some of it opens the calcium gate in the sarcoplasmic reticulum. So the twitch does not start, and this picture doesn't really draw it correctly, but the twitch should not start until calcium starts coming into the cell. Notice the twitch is also very long. A cardiac muscle fiber twitch can be about 250 milliseconds, kind of the same length as the action potential, right? So what does that mean? The reason why the action potential is so long is to prevent summation of twitches. Now, the value of that may not be entirely evident, so let me go ahead and try and explain it. In order for the heart to work, we need to be able to contract, to generate tension and push blood out, and then relax, right? So contract, relax, contract, relax. If I summate twitches, it's going to be like this. I have to let my heart relax every single time. The twitch has to end so that my heart can refill with blood and I can push it out again. So if my heart were exhibiting tetanus, it would not be doing its job. It would stop moving blood because it would be in a perpetual state of, that's not moving any blood. So therefore, it is imperative that twitches do not summate in cardiac muscle. And the fact that the action potential is this long actually helps with that because it means the refractory period is incredibly long. The yellow area here is the refractory period. It is an absolute refractory period. There's no relative refractory period in this case. So the most that we could get here is 2 twitches side by side where one almost completely relaxes before the second one starts. Now look at the time here. This is 250 milliseconds for a twitch. So how long is that? That is 1/4 of a second. So how many twitches could you hypothetically fit in a second? 4 of them, right? So how many beats can your heart have in a second? Well, the maximum is 4. So what does that translate when we think of beats per minute? If there are 60 seconds in a minute and we can have up to 4 beats per second, then that's 240 beats per minute. So the fact that the twitch itself is 1/4 of a second and there's an absolute refractory period that's also 1/4 of a second means that we have a natural cap on our heart rate. We cannot go above 240 beats per minute. And as we age, our cap is significantly lower than that. All right, so that concludes this lecture. I'll see you in the next cardiac lecture.